I'm here with Philipp Heck, who is the Robert A. Pritzker Associate Curator of
Robert A. Pritzker Associate Curator for Meteoritics and Polar Studies.
There.
I practiced this many times.
Yeah. Today we're going to talk about the age of the solar system.
These large, white, aluminum-rich inclusions that you can see here, these are the oldest minerals that formed in the solar system, and they can be dated. And it's basically the start of the solar system. We call it T0, time zero. It's 4.567 billion years. It's an easy number to remember, 4.567 billion.
We know how old the solar system is because of this specific specimen.
Exactly. This defines T0. When I give public talks, I usually give people a slice in a plastic, and I say you can hold the oldest piece of material in the solar system, and even you don't see it, but it is the oldest material available to anyone on this planet is in there. There's nothing older that you can touch.
Wow.
Pre-solar grains. They're older than the sun, older than the meteorite itself. Some of them might be as old as 5.5 billion years.
Wow. And how do you know that?
So these pre-solar grains, they can be analyzed chemically. And their isotopic composition is highly anomalous, very different from anything in the solar system. Their composition cannot be explained by any process that can occur in the solar system. The fact that they are embedded in that rock tells us they could not have been incorporated later. They must have been part of that mixture from which the rock formed. And since the rock formed 4.6 billion years ago, they must be older.
Older than 4.6 billion years.
And some minerals even can be dated. So far we have only dated approximately 30 grains. Most of them are about 200 million years older than the sun. And a few of them are about 1 billion years older than the sun, which makes them about 5.6 billion years old. We think the solar system formed basically from a cloud of gas and dust. And this cloud of gas and dust formed from different sources, from different stars. Some of these stars were indeed stellar explosions, supernovae. Mm-hmm. They exploded, and during these explosions, new elements formed. And after the matter cooled down, some of this matter condensed as gas. There were other stars, many other stars, which were like the sun, but they were already at the end of their life. They expanded, became red giants, and expelled the matter into space. And from all these mixtures of stellar ejecta, this pre-solar cloud formed. Within this pre-solar molecular cloud, the protosolar disk formed. It's basically a rotating disk of gas and dust. The protosun formed, and later the sun. Planetary building blocks formed. Most of the matter was altered, heated. The pre-solar signature is not visible anymore. But some of this pre-solar matter survived without having been altered. That's what's trapped in here. It's only a tiny fraction. The most abundant type of pre-solar materials are diamonds, nanodiamonds. These diamonds are tiny. They are only 2 nanometers across, maybe consist of 1,000 to 2,000 carbon atoms. We can extract them from meteorites, and we basically dissolve everything else. Just are left with the acid residue of diamonds, and in this little vial I have billions of diamonds. You normally wouldn't see them because they're so small you wouldn't scatter light, but they clump together, so you can see that white residue.
Yeah.
And these are all diamonds. It's literally stardust.
It's awfully ethereal looking. It's kind of like floats around in this nebulousness.
These diamonds, they were discovered in Chicago in 1987 at the University of Chicago with a Field Museum meteorite.
Really? It's overwhelming. It's how did you get into this?
Yeah, so when I heard about this first, I was extremely fascinated, and I heard about it when I was a student of earth science in Switzerland, and did an undergraduate project in a cosmochemistry lab there. I said, oh, this is so fascinating. Would it be possible to do a PhD there?
Yeah.
And this because I was completely hooked. I was always interested in astronomy, and volunteered at the local observatory there. And I thought, oh, if I could do that for a living, that would be fantastic. And yeah, actually the opportunity came up, and I was able to work on the Stardust for my PhD.
Really?
And everything, yeah. So I'm very fortunate to work on such a very, I would say, on the oldest matter that is available anywhere on this planet. It keeps us very motivated, and it's really great.
Yeah.
With every question that you answer, you open 10 more questions that can be studied. But then you have to make a wise decision which questions are actually worth pursuing to answer, worth the time and money. And one of these is actually the origin of those nanodiamonds, because nanodiamonds are basically pure carbon. And they survived the formation and evolution of our solar system. And almost nothing else did survive. Almost everything has been altered. So the carbon in our body, on our skin, you don't see a pre-solar signature anymore, although it might have the same origin as these diamonds.
So the carbon that makes up those diamonds is the same carbon that makes up the carbon within me and you.
Exactly.
And all of life on Earth.
Exactly.
So this is like our great times infinity, great ancestor, essentially.
Yeah, so I think we have a common origin, these diamonds and life on Earth. And this is a proxy of, it's basically the tiny fraction that survived all these billions of years since the planets and the Earth formed. And by studying those diamonds, they open up they're like a time capsule. By studying them, we can learn about the past, about the time before the solar system.
So if you were to take those diamonds down to a pawn shop, how much is one of them worth?
You would not even know.
I don't know. But I always tell, they probably wouldn't make nice engagement rings because they're so small.
Yeah.
But there are millions.
It still has brains on it.